Hello, this is Anthony Schmitt for ME3708 Machine Design. I'm here to do video topic number 2. It's on static failure. Let's get started. So materials will undergo different behaviors during deformation. As covered in the previous video topic, there's elastic and plastic deformation. With elastic, the material returns to its original size and shape after stress is removed. With plastic, the material does not return to its original shape and size, so it's deformed and stays deformed. Yield stress, shear stress, is important for yielding. One way we can simulate this is with a tensile test to show the yielding. Stress behavior, it depends on the loading condition. Oftentimes we'll show the loading with a block like this, and then this will show the stress graph, and we can have our stress, the Y, the X, and the Z, and we can even have torsion along the axes. There's 3 yielding criteria. There's maximum shear stress criterion. There's the octahedral shear stress / distortion energy criterion, and the Coulomb-Moore theory. With the max shear stress criterion, the factor of safety, N, is equal to the yield strength over 2 over tau max. And there's a process to find tau max and then and then put it in the equation for N to solve for N. But to solve for tau max, we take theta 1 and theta 2, we use this equation to solve for theta 1 and theta 2, and then tau 1 and tau 2, and then we'll draw a Moore circle using those and find where tau max is. And then once we find tau max, we can then go and calculate N. For the octahedral shear stress distortion energy criterion, the factor of safety, N, is the yield strength over the von Mises stress, sigma prime. And to calculate sigma prime, use one of these equations. There's 3D using theta 2, 1, 2, and 3, and then 2D with A and B, and then there's 3D with X, Y, and Z, theta, tau, X, Y, and Z, and with 2D as well. So you can find it with 1, 2, and 3, or with the X, Y, and Z stresses. And the last one is the Coulomb-Moore theory. This equation is sigma 1 over S of T minus sigma 3 over S of C equals 1 over N. And then you'll find your safety factor with that. And what we have here is the Coulomb-Moore failure curve, and it's a graph of the different stresses and the curve that they end up with. Next we have brittle material failure. Ductile materials experience shear stress, which causes yielding, but more brittle materials, they experience normal stress, which causes fracture. Sort of the difference there. So ductile material will experience the shear stress and it'll yield, but it will also fracture eventually, while a brittle material will fracture with little to no yielding at all. So to illustrate that, we have a highly ductile material here. You can see it originally started as a cylinder like this, but the deformation caused it to yield and then eventually fractured. And then with the very brittle material, it didn't yield at all. It still got its original shape, but it fractures. Here's the brittle failure modified Mohr's circle. With brittle failure, the Mohr circle is going to be not really a circle, clearly. So because it doesn't experience like a smooth yield deformation before it fractures, it just fractures. So obviously a different